In the early decades of the 20th century, the universe seemed to most astronomers like a grand stage set in permanence. Stars sparkled in the dark. Galaxies were not yet known to be separate islands, and many still believed that the cosmos was unchanging and eternal. Even Einstein himself, when writing his great equations of general relativity, added a special balancing term called the cosmological constant, so that the mathematics would yield a universe that stood still. It was an instinct born of centuries of philosophy, from Aristotle to Newton, to imagine that the heavens were fixed, calm, and timeless. But reality has a way of resisting human preference. High in the mountains of California, at the Mount Wilson Observatory, a man named Edwin Hubble began examining faint smudges in the sky with the 100-inch Hooker telescope, the largest in the world at that time. Hubble was not looking for poetry, he was measuring the brightness and distance of galaxies. He applied the work of Henrietta Leavitt, who had discovered that certain pulsating stars called Cepheids could serve as reliable cosmic mile markers. By comparing the apparent brightness of these stars to their intrinsic brightness, distances could be measured across vast gulfs of space. As Hubble catalogued the distances of these galaxies and compared them to the light they emitted, a strange pattern emerged. The spectral lines of their light were shifted toward the red. It was as if the light waves had been stretched in their journey across the cosmos. This redshift was not a trivial detail. It was a clue written into the fabric of starlight itself. And when Hubble plotted distance against velocity, he discovered that the farther a galaxy was, the faster it seemed to be receding from us. The result was astonishingly simple. A linear relationship that came to be written as velocity equals Hubble constant times distance. In words, the farther away a galaxy is, the faster it recedes. This was not the discovery of motion through space, like cars retreating along a road. It was the discovery that space itself was stretching. Imagine the surface of a balloon with dots on it. As the balloon inflates, the dots move away from one another. Not because they are traveling on the surface, but because the surface itself expands. In the same way, galaxies are not flying through space away from us, but rather the universe itself is growing, and the galaxies are being carried along by this cosmic expansion. The implications struck at the heart of human assumptions. If the universe is expanding today, then in the past it must have been smaller. And if you go back far enough, billions of years into the past, all of space, time, matter, and energy must have once been compressed into a state of extraordinary density and heat. The discovery carried within it the seeds of what would later be called the Big Bang. A cosmos with a beginning. A cosmos with an unfolding story. For Einstein, this was unsettling. His equations had predicted something like this all along, but he had resisted it. Upon learning of Hubble's discovery, he reportedly called his earlier insertion of the cosmological constant the greatest blunder of his life. In truth, the story was subtler, but the sentiment captured the shock of realizing that the universe was not static, but dynamic. Reality was larger, stranger, and more dramatic than even the most brilliant minds had anticipated. This expansion was not merely a matter of academic record. It meant that the very stage on which all of existence plays out is changing beneath our feet. Distances grow, not because objects move, but because the fabric itself stretches. The night sky, which feels to the human eye so serene and eternal, is in fact restless. Galaxies recede, clusters drift apart, and the scale of the cosmos increases with every passing second. Yet a profound question emerges. If space is stretching, does that stretching weaken gravity? Gravity is the great sculptor of the universe, the invisible architect binding planets into orbits, holding stars within galaxies, and galaxies within clusters. But if the fabric itself expands, then what becomes of the threads of gravity woven through that fabric? Is the hand that binds strong enough to resist the tide that pulls everything apart? The tension between these two forces, the pull of gravity and the push of expansion, would define not only the structure of the universe, but its fate. To explore it is to enter a cosmic drama where equations become characters, where the curvature of space-time itself contends with the stretching of the void, and where human understanding must continually grow to keep pace with the enormity of creation. The story begins here, in the flicker of distant galaxies whose light carries the memory of expansion. The discovery that shattered the illusion of a static universe and opened the way to new questions that remain as urgent today as they were in Hubble's time. If space grows, what happens to the forces that hold it together? Does gravity weaken, or does it find ways to endure? The next step in this story is to look at how gravity itself is understood, not as a mysterious force pulling across emptiness, but as the very geometry of space-time revealed by Einstein. And in that revelation, the dance between expansion and attraction begins to take shape. The universe, as revealed by Hubble, was no longer a fixed arena, but a restless ocean. Yet, to fully grasp the weight of this discovery, we must turn to gravity itself. For gravity is not simply another force among forces, it is the silent framework upon which the entire cosmos unfolds. For centuries, it had been thought of in Newtonian terms, an invisible pull reaching across emptiness, acting instantaneously between masses no matter how far apart they might be. In this picture, the sun pulls on the Earth pulls on the moon, and every particle of matter in existence exerts a force upon every other. It is an elegant image, one that explained the motions of the planets with stunning accuracy, but it left unanswered the deeper question of what gravity really is. Einstein's general theory of relativity reframed that question. In his vision, gravity is not a force at all, but the manifestation of curved space-time. Matter tells space-time how to curve, and space-time tells matter how to move. Imagine a fabric stretched taut, with a heavy sphere pressing down upon it. The depression is not a force in itself, yet smaller spheres rolling nearby will spiral toward the mass because they follow the natural lines of the fabric. This is how planets orbit the sun, not because of an invisible pull, but because space-time itself bends around the star. This new conception of gravity was more than a redefinition, it was a revelation. It implied that space and time are not passive backgrounds, they are dynamic participants in the cosmic story. When Hubble's discovery of expansion is placed in this context, the picture becomes even more profound. If space can stretch, and if gravity is the geometry of that space, then the two phenomena are not separate but intertwined. Expansion is not something happening outside of gravity's reach. It is part of the same fabric. Consider what this means for the galaxies drifting apart. They are not receding through an empty stage, they are following the stretching of the very grid lines that define existence. Gravity works within this expansion, shaping local structures, bending trajectories, and anchoring matter even as the larger fabric elongates. It is as if the universe itself is both sculptor and stage, creating and expanding simultaneously, while gravity and expansion act as the twin weavers of cosmic destiny. Yet the image is not one of simple balance. On the smallest scales, gravity reigns supreme. Atoms remain bound. Stars fuse within their cores. Planets circle faithfully around their suns. The expansion of the universe does not reach into the heart of an atom or stretch the orbits of worlds. Those systems are bound. Their internal force is far stronger than the subtle stretching of cosmic fabric. The Earth does not drift from the sun because space-time is expanding, nor do galaxies dissolve into nothingness. Expansion acts gently across immense distances, revealing itself only on the grandest scales of intergalactic separation. This realization leads to a critical distinction. There are bound systems, where gravity or other forces such as electromagnetism hold matter tightly together, and there are unbound systems, where matter drifts with the flow of cosmic expansion. Galaxies and clusters of galaxies form knots in the fabric, resisting the stretch, while the vast voids between them widen. Expansion is not uniform in its effect. It is selective, sculpting structure by allowing bound islands of matter to persist, while unbound regions grow emptier. But this picture was not complete until a later, deeper discovery came into view. For in the 1990s, astronomers found that expansion was not merely continuing, it was accelerating. Something unseen was pushing galaxies apart with increasing speed. This mysterious phenomenon was named dark energy, a term that conceals more than it reveals. It is not energy in the ordinary sense, but rather a property of space-time itself, acting like a negative pressure, as though the vacuum has a tendency to stretch. The discovery of dark energy reframed the balance between gravity and expansion once again. Gravity pulls, but dark energy pushes harder across the larger scales. This changed the stakes of the cosmic story. It was no longer a simple question of whether expansion would slow and perhaps reverse under the pull of gravity, collapsing into a future big crunch. Instead, it became clear that the universe would likely continue expanding forever, with galaxies drifting beyond one another's horizons until their light could no longer reach us. Gravity, the eternal binder, would never again draw the whole universe back into itself. The cosmic tug-of-war tilted in favor of expansion, driven by an invisible presence that resided not in matter, but in the vacuum of space. The mathematics of this is captured in the Friedmann equations, which describe how the scale factor of the universe changes over time. These equations balance the density of matter, the curvature of space, and the influence of dark energy. They show in rigorous form what the observations reveal in light, that the destiny of the cosmos depends on this interplay. And yet, for all the clarity of the equations, the mystery of dark energy remains. We do not know its nature, only its effect. It is as though the universe is whispering a secret in a language we cannot yet translate, telling us that its expansion is not just a gentle drift, but an accelerating tide. As the story unfolds, we are left with an ever-deepening question. If the universe is not static, if it expands and accelerates, and if gravity is both the geometry and the sculptor within this expansion, then what is the true fate of bound structures, of galaxies, of clusters, of the cosmic web itself? Will gravity hold, or will the stretching fabric of space-time ultimately tear even the most intimate bonds apart? The universe is both expanding and curving, stretching and binding, and we are caught between those two motions. It is a dance whose steps reach from the atomic to the cosmic, and whose rhythm is measured in billions of years. From Hubble's telescope to Einstein's equations, from the galaxies we see to the dark energy we cannot see, the narrative continues to unfold. The next part of this chapter deepens the paradox, examining more closely why some systems resist expansion while others yield, and how the tug between gravity and cosmic stretching shapes the very structure of the universe we inhabit. The universe we inhabit is a tapestry woven by two opposing tendencies, the pull of gravity and the push of expansion. To walk further into this mystery, imagine again the galaxies scattered like lights across the night sky. They seem still to the human eye, frozen against the blackness, yet every one of them is in motion. Expansion carries them apart, yet within those galaxies stars circle their centers, and within those stars, atoms fuse. This paradox lies at the heart of cosmic reality, that expansion acts everywhere, and yet it does not destroy the local bonds that hold matter together. Why is it that atoms do not swell? That the Earth does not drift from the sun? that the Milky Way does not unravel with every passing billion years? The answer lies in the strength of forces and the scale at which expansion becomes significant. Electromagnetic forces within atoms are far stronger than the subtle stretching of space, ensuring that electrons remain bound to nuclei. Gravitational forces within galaxies, though weaker in absolute terms, are sufficient to anchor billions of stars together against the background drift. Expansion is real, but it is faint compared to the bonds within these systems, like a tide that cannot dislodge stones fastened to the shore. Astronomers distinguish between bound and unbound systems. A bound system is one where the mutual forces between its parts are stronger than the rate of expansion. A solar system is bound. A galaxy is bound. Even clusters of galaxies, containing thousands of members, are bound. But the regions between those clusters, the enormous dark voids, are unbound. There, the expansion of the universe carries matter apart, and over billions of years those voids grow larger, while clusters remain as islands separated by ever-widening seas of emptiness. This selective action gives rise to the cosmic web, the vast filamentary structure revealed by surveys that map the distribution of galaxies. What appears at first glance as a random scattering of stars resolves into a pattern. Galaxies are strung along filaments, clumped into clusters, woven into sheets, and separated by immense voids where almost no galaxies reside. This is the shape of the universe on its largest scales, a web sculpted by gravity yet stretched by expansion, a cosmic architecture more intricate than any cathedral built by human hands. Expansion has been present since the beginning, yet its effect has changed over time. In the early universe, matter was dense and gravity was strong enough to slow expansion, allowing structures to form. Without this slowing, galaxies and stars would never have condensed. Later, as matter grew more diluted, dark energy began to dominate, pushing galaxies apart with increasing speed. The balance between attraction and repulsion shifted, and the universe entered an era of accelerated expansion. This shift is not just an academic detail, it determines the ultimate fate of everything we see. If expansion continues to accelerate indefinitely, galaxies beyond our local group will eventually slip over a horizon, not because they move faster than light, but because the fabric between us and them stretches so quickly that their light will never reach us. The night sky would grow lonelier, with only the faint glow of the Milky Way's remnants visible to distant descendants. Gravity will still bind what it can, but the stage around those bound systems will continue to expand without limit. The thought is both scientific and profoundly human. On one hand, it is a calculation written in equations of cosmology, balancing densities and pressures in the Friedmann models. On the other, it is a vision of impermanence, that even the largest structures are not eternal, that the universe itself moves towards solitude. The galaxies we see tonight are companions only for a time. Their light is a fleeting gift, a message sent across billions of years that may someday be beyond our reach. This realization reframes the way we think of gravity. It is not only the architect of local structures, it is also the guardian against expansion, the hand that holds matter together in the face of a stretching void. Yet it is not omnipotent. On the scale of the cosmos, expansion wins, not by shattering bonds directly, but by carrying unbound regions ever further apart. Gravity works locally, expansion acts globally, and together they choreograph the evolution of the universe. And so the chapter closes on a vision of contrast. On scales of atoms and planets and galaxies, gravity rules, giving shape to the world we know. But on the grand canvas of the cosmos, expansion dictates the story, pushing everything outward, redshifting the light of galaxies, sculpting voids, and setting the stage for the universe's ultimate fate. What began with Hubble's discovery has become a tale of dual forces, one pulling, one stretching. and humanity caught in the middle, striving to understand their endless dance. The next chapter turns fully to gravity itself, not merely as a pull or a bend, but as the deep structure of reality that Einstein unveiled. For only by grasping the true nature of gravity can we understand how it interacts with the expansion of space and how together they shape the destiny of all things. To speak of gravity is to speak of the oldest and most familiar of natural forces, yet also the deepest and most mysterious. From the earliest days of human thought, when philosophers watched the fall of an apple or traced the wandering paths of planets, there was a recognition that something unseen governed the motions of the heavens. For Isaac Newton, gravity was the invisible thread binding the cosmos. He gave it mathematical form in his law of universal gravitation, stating that every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of their distance. This simple law explained the orbits of planets, the tides of the seas, and the fall of bodies on Earth with breathtaking precision. It turned the cosmos into a machine whose gears were predictable and whose parts obeyed mathematical regularity. But Newton's description, as powerful as it was, carried unanswered questions. How could a force act instantly across empty space? How did one mass know the presence of another, light years away? The law worked, but it lacked a mechanism. To Newton himself, this was troubling. He gave the world a formula that governed gravity, but he did not explain what gravity was. The stage of the universe, in his view, was absolute space and absolute time, unchanging backdrops upon which matter moved. Gravity acted within this framework, but remained, at its heart, a mystery. In the early 20th century, Albert Einstein dared to reimagine the very stage. Building upon his special theory of relativity, which had already united space and time into a single continuum, he proposed that gravity was not a force at all, but the manifestation of curved space-time. In this new vision, masses do not reach across emptiness to pull one another. Instead, matter tells space-time how to curve, and curved space-time tells matter how to move. The planets do not orbit the sun because of an invisible tether, but because the sun bends space-time around it, and the planets follow the natural paths of that curved geometry. To picture this, imagine space-time as a vast fabric stretched taut. Place a heavy ball on the fabric, and it sinks, creating a depression. Smaller balls rolling across the surface follow curved trajectories around the central mass. This is an image often used in classrooms, though imperfect, for real space-time curves not downward into some outside dimension, but within itself. Still, the analogy conveys the essential point. Gravity is not a pull, it is geometry. It is the shape of reality itself. Einstein captured this with equations that are among the most elegant in all of physics, the field equations of general relativity. These equations describe how energy and momentum determine the curvature of space-time, and in turn, how that curvature dictates the motion of matter and light. They replace Newton's instantaneous action at a distance with a dynamic, local interaction. Changes in mass distribution ripple through space-time at the speed of light, producing phenomena such as gravitational waves, ripples in the fabric that were only directly detected a century later. This new conception answered Newton's old puzzle. There is no mysterious force reaching across emptiness. There is space-time, and it is not passive. It bends, it stretches, it flows, it evolves. Under Einstein's vision, the universe itself became a living stage, one that responds to its contents. Stars, planets, and galaxies all shape the arena in which they move, and their motions in turn are shaped by that arena. The cosmos became not a machine upon a rigid platform, but a symphony in which space and time are instruments as alive as the matter and energy they host. The human meaning of this is profound. To look into the night sky is to look into a structure that is not fixed but dynamic. Every beam of starlight bends as it passes near masses. Every path of every body curves along the hidden architecture of space-time. Even time itself is not absolute, but stretches and contracts depending on gravity. A clock on the surface of the Earth ticks more slowly than a clock in orbit, not because the mechanisms differ, but because the flow of time itself is altered by the Earth's mass. This realization dissolves the old idea of gravity as an external actor. There is no outside force. There is only the shape of reality. When you stand upon the Earth, you are not being pulled downward. You are following the natural path through curved space-time, a path that happens to press against the surface. The floor pushes upward, resisting your fall, and you interpret that as weight. But in truth, the motion is determined by the geometry of the cosmos itself. Here, the connection to expansion becomes clear. If space-time is the arena and gravity is its curvature, then expansion is simply another mode of behavior of that arena. Space does not merely bend around masses, it also stretches on the largest scales. Gravity and expansion are not separate phenomena, but two expressions of the same fabric. One acts to curve, to bind, to bring together. The other acts to stretch, to dilute, to push apart. Both are written in the language of geometry. Both are revealed in the equations of general relativity. Einstein's theory was tested again and again. Starlight bent during an eclipse, just as predicted. The orbit of Mercury, with its strange precession, found its explanation. Time dilation near massive bodies was measured with precision clocks. Each success confirmed that gravity is not a force in the Newtonian sense, but a manifestation of space-time itself. And yet, for all its triumphs, general relativity also revealed the immensity of what we do not know. For within its equations lie singularities, places where curvature becomes infinite, such as the centers of black holes. And beyond them, on the largest scales, lie questions of expansion, acceleration, and dark energy. The union of Einstein's gravity with Hubble's expansion reshaped cosmology into what it is today. The universe is not a fixed stage, but a dynamic entity, curving and stretching in response to its contents. And humanity, perched on a small planet around an ordinary star, has come to see not only the motions of objects, but the motions of space-time itself. As we move forward, the story deepens. We must explore why expansion does not tear apart the bonds of atoms, why galaxies remain intact, and why gravity still holds sway locally, even as the universe grows. For it is in the distinction between bound and unbound systems that the dance of gravity and expansion reveals its intricate steps. And in that dance, the structure of the cosmos is born. Gravity in Einstein's universe is not only geometry, but a living fabric that records every presence of matter and every shift of energy. To understand its meaning more deeply, consider a beam of light traveling through space. According to Newton, light would move in straight lines, unaffected by gravity because it has no mass. Yet, Einstein's theory predicted otherwise. Light, too, must follow the curvature of space-time. When starlight passes near the sun, its path bends. This is not because the sun pulls on it with force, but because the straightest path through curved space-time is itself bent. In 1919, during a solar eclipse, astronomers observed the positions of stars near the sun, appearing slightly displaced, exactly as Einstein predicted. It was the first great triumph of general relativity, a moment when the universe confirmed the new vision of gravity as curvature. Time, too, bows to gravity. Place two identical clocks, one on the surface of the Earth and one high in orbit. The one closer to Earth's mass ticks more slowly. This phenomenon, called gravitational time dilation, is not a trick of perception. It is reality. The flow of time itself runs at different rates in different gravitational potentials. Without accounting for this, the global positioning system would fail within hours, as the satellites above our heads experience time differently than receivers on the ground. The fact that we can navigate streets with precision owes itself to Einstein's insight that time is not absolute, but part of the fabric shaped by gravity. General relativity also explains why black holes exist. When enough mass collapses into a small enough region, the curvature of space-time becomes so extreme that nothing, not even light, can escape. At the event horizon of a black hole, paths that would normally lead outward now curve inexorably inward. The geometry itself closes off escape. Inside, space-time curves toward a singularity, a point where our equations break down and our understanding ends. In black holes, gravity reveals both its greatest strength and its greatest mystery, exposing the limits of current human knowledge. This reshaping of gravity changes how we think of expansion as well. If space-time itself is dynamic, if it can bend and ripple, then it can also stretch. The expansion discovered by Hubble is not something outside of Einstein's theory, but something woven into it. Indeed, solutions to the field equations describe universes that expand, contract, or remain static depending on their contents. The equations allow for a cosmos that evolves, one that has a past, a future, and perhaps a destiny determined by the balance between matter, radiation, dark energy, and curvature. This leads to a remarkable unity. Gravity is not separate from expansion, it is the language in which expansion is written. The same mathematics that explains why apples fall and planets orbit also explains why galaxies drift apart. The same fabric that bends around stars stretches across billions of light years. Expansion is not a separate actor, it is a mode of behavior of space-time itself. To grasp this is to see the cosmos not as a collection of parts governed by disconnected laws, but as a single whole whose architecture is both intimate and vast. The beauty of this vision is that it links the human scale with the cosmic. The weight you feel standing on Earth, the tick of a clock, the bending of starlight, the growth of voids between galaxies, all are facets of the same reality. Gravity is the quiet thread running through every aspect of existence. And yet, the more we understand it, the more questions arise. If expansion is part of gravity, what determines whether bound systems resist or yield? If the universe stretches forever, what becomes of the galaxies, the stars, and the very atoms of which we are made? These questions lead directly to the next step. To understand the interaction of expansion and gravity, we must distinguish between the systems that remain intact and those that are swept apart. This boundary between bound and unbound will reveal not only why the cosmos looks as it does today, but also how it will evolve in the ages to come. Einstein's vision of gravity reaches its most powerful expression when placed against the backdrop of the entire cosmos. For once, we accept that space-time itself can curve, ripple, and expand. Then the very distinction between motion and stillness dissolves. A galaxy does not move away from us through emptiness. Instead, the distance grows because the fabric in between stretches. A planet does not orbit because it is tugged by an invisible hand. It follows the straightest possible path through a geometry curved by the sun. Gravity and expansion are two manifestations of the same structure, two aspects of the living fabric of reality. To appreciate this unity, imagine the cosmic timeline unfolding. In the earliest moments after the Big Bang, matter and energy were compressed into a density beyond comprehension. Space was curved everywhere, time flowed differently at every point, and the expansion was so rapid that entire regions of the universe slipped from causal contact with one another. Yet within that expansion, gravity began its patient work, pulling matter together into clumps, igniting the first stars, forming galaxies. From the fireball of creation, order emerged, not despite expansion, but in concert with it. The tension between gravity and expansion can be thought of as a cosmic dialogue. Expansion drives matter apart, gravity gathers it. Without expansion, the universe would have collapsed long ago into a single dense state. Without gravity, matter would never have clumped, and the universe would be a thin mist of particles drifting forever. Both are necessary. Both are written in the same equations. Both are inscribed into the very structure of space-time. Consider also the way relativity unites scales. On Earth, you feel your weight because your body presses against the ground, resisting the natural freefall that would carry you along curved space-time. In orbit, astronauts feel weightless, not because gravity vanishes, but because they follow space-time's curve without obstruction. Their path is free, and so they feel no resistance. This is the same principle that governs galaxies, the same principle that describes the bending of light and the stretching of space. From the smallest scales of daily life to the grandest scales of the universe, gravity is geometry. And yet, even as general relativity provides such a powerful framework, it also whispers of incompleteness. At the centers of black holes, singularities appear where curvature becomes infinite. At the birth of the universe, another singularity marks the limit of our understanding. In these places, relativity cannot be the whole story. To truly know gravity, we must someday unite it with quantum theory, weaving together the geometry of space-time with the probabilistic fabric of the quantum world. But that unification remains beyond reach, leaving us with a theory that is astonishingly accurate, yet still unfinished. For now, relativity remains our best guide. It tells us that gravity and expansion are not rivals, but partners in shaping the cosmos. It explains why bound systems can exist within an expanding universe, and why the expansion reveals itself only across the greatest distances. It teaches us that the stage is alive, that the universe is not a container, but a participant, that reality itself bends and flows in response to matter and energy. The human resonance of this vision is immense. We live not on a passive platform, but within a dynamic architecture. Every second, space-time curves beneath our feet and stretches beyond our sight. We are passengers in a universe that evolves, not only in its contents, but in its very structure. To know this is to step outside the ancient illusion of permanence and to embrace the truth of motion written into the cosmos itself. And so the chapter closes where it began, with the recognition that gravity is not a force, but the shape of reality. Newton gave us a picture of invisible pulls, a cosmos bound by action at a distance. Einstein gave us a vision of curvature, a cosmos whose stage is as alive as its players. When we place this vision beside Hubble's discovery of expansion, the story deepens. Expansion and gravity are not two separate phenomena. They are two sides of the same coin, two expressions of the geometry of space-time. The next step is to understand how these forces play out in practice, why some systems resist expansion while others are swept along, and how this boundary between bound and unbound shapes the very structure of the universe. In a universe that expands, the natural question arises: why does not everything expand along with it? If galaxies drift apart, why do the stars within them remain bound? If space stretches, why do planets still circle their suns with steady rhythm? And why do atoms hold their electrons as tightly as ever? To answer this, we must draw a boundary between what is bound and what is unbound, between what resists expansion and what yields to it. Begin at the smallest scale. Atoms, the building blocks of matter, do not grow as the universe expands. The reason is strength. The electromagnetic force that binds electrons to nuclei is immensely powerful compared to the subtle stretching of space-time. Imagine trying to pull apart a grain of sand with a breeze that blows faintly across a desert. The grain is unmoved. The expansion of the universe is real, but its effect on atomic scales is negligible. The same applies to molecules and the intricate structures of biology. Life thrives in defiance of cosmic expansion because the forces that govern chemistry overwhelm the faint tug of a growing cosmos. On the scale of planets and stars, gravity replaces electromagnetism as the binding force. The Earth orbits the Sun not because of some fragile balance, but because gravity's pull is far stronger than the expansion across such a small distance. Space may stretch, but it stretches gently, and within the solar system, the effect is imperceptible. The Earth will not drift outward, nor will the Moon escape its orbit, for the gravitational bonds are far too strong. Expansion does not pry open systems so tightly held. Galaxies tell the same story on grander scales. Hundreds of billions of stars orbit the center of the Milky Way, bound by the combined gravity of visible matter and the vast halo of dark matter. The distance across a galaxy is measured in tens of thousands of light years, and yet expansion cannot undo its cohesion. Galaxies persist as islands in the cosmic ocean, resistant to the tide. Clusters of galaxies, though larger still, also remain bound. The pull of their combined mass anchors thousands of galaxies together. Even as the universe expands, these clusters stand as strongholds of gravity. The place where expansion reveals its hand most clearly is in the space between clusters. There, gravity is weak, matter is sparse, and no binding force resists the stretching. Over billions of years, these regions widen into vast voids. Galaxies at the edges recede from one another, and filaments of the cosmic web grow longer and thinner. Expansion does not act by tearing apart the strong, but by amplifying the distance between the weakly bound. It is here that the fabric stretches, here that the universe grows, here that the distinction between bound and unbound becomes vivid. This distinction shapes the very architecture of the cosmos. Surveys of galaxies reveal a web of filaments and clusters surrounded by emptiness. The pattern arises from gravity's ability to hold some regions together while expansion pulls others apart. It is as though the universe is a sponge, with dense knots where matter clings and vast voids where it recedes. Without expansion, everything would collapse into uniform clumps. Without gravity, everything would drift into uniform mist. Together, they create a balance that sculpts the web of galaxies stretching across billions of light years. The human meaning of this is striking. The structures we know, from atoms to galaxies, exist because they are bound. The universe is not a chaos of ceaseless stretching, nor is it a prison of total collapse. It is a mixture. Some bonds endure, others surrender. In that mixture lies the possibility of stars, planets, and life itself. We exist because gravity and expansion share the cosmos, each claiming its domain, neither absolute. The story of bound and unbound systems is also a story of time. In the early universe, matter was dense, and gravity reigned almost everywhere. Over time, as space expanded and matter thinned, expansion gained the upper hand across greater distances. Today, galaxies remain bound, but clusters drift further apart. In the distant future, even the galaxies we now see may vanish beyond our horizon, leaving only our local group as a remnant island in a growing sea of emptiness. The line between bound and unbound is not fixed, but shifts as the cosmos evolves. And so the chapter begins with a simple question: why does not everything expand? And ends with a deeper understanding of how the universe is sculpted. The cosmos is not uniform in its response to expansion. Some systems cling, some yield, and between them emerges the grand structure of all that is. The next step is to follow this realization into the realm of dark energy, the mysterious force that accelerates expansion and tips the cosmic balance further, raising questions not only about what is bound today, but about what might remain bound tomorrow. Bound systems reveal themselves not by resisting expansion with conscious effort, but by the quiet dominance of their own internal forces. Think of a galaxy cluster. Within it, thousands of galaxies orbit a shared center of mass, bound by gravity so strongly that expansion cannot pry them apart. Yet between clusters, where matter is thin and the bonds are weaker, space stretches relentlessly. Over billions of years, the voids widen, creating the vast dark gulfs that define the cosmic web. This is how the universe sculpts itself, not by tearing everything open at once, but by choosing where expansion takes hold and where it does not. Astronomers often illustrate this difference with the analogy of coins glued to a balloon. As the balloon inflates, the coins remain the same size, even as the distance between them increases. The glue in this image is the force that binds, whether electromagnetic inside atoms or gravitational inside galaxies. The inflation of the balloon represents expansion, a stretching of the underlying surface. This simple picture captures why bound systems persist while the larger scale expands, though in reality the universe is vastly more intricate, filled with forces, dark matter, and energies unseen. The role of dark matter here cannot be overstated. Ordinary matter alone would not be enough to hold galaxies together. Stars orbiting near the edges of galaxies move too quickly, as if pulled by an unseen hand. This unseen component, called dark matter, provides the extra mass needed to bind galaxies and clusters. Without it, expansion might have dissolved many structures long ago. Dark matter, invisible yet essential, acts as the glue that keeps galaxies whole, ensuring that bound systems endure despite the cosmic stretching. This endurance is not absolute, however. Expansion still alters the landscape of the universe, even if it leaves the insides of galaxies untouched. Over time, the space between galaxy groups grows. Already, our own local group, which includes the Milky Way and Andromeda, is bound tightly enough that its members will not drift apart. In fact, the Milky Way and Andromeda are on a collision course, destined to merge in several billion years despite expansion. But beyond the local group, galaxies slip away, their light stretching into red, growing fainter, until one day they will no longer be visible at all. Our sky will grow emptier, not because galaxies vanish, but because expansion has placed them forever beyond reach. This perspective reframes our place in the universe. We live in a bound oasis within an unbound sea. Our galaxy and its neighbors form a small island, preserved by gravity against the tide. But that tide is real, and it carves the cosmos into isolated archipelagos. Each bound region becomes its own universe in practice, separated from others by gulfs so wide that no signal can cross. This future of isolation is the direct consequence of the boundary between bound and unbound. There is also a philosophical depth here. Expansion reveals that permanence is an illusion, that bonds are always relative to scale and time. Atoms will not expand, but galaxies will drift. Galaxies will endure, but clusters will separate. Even the cosmic web, magnificent though it is, will thin and stretch as the voids expand. What we call a structure is temporary, a balance between forces that may shift as the universe evolves. To know this is to understand that existence itself is a play between binding and letting go. And so the narrative of bound and unbound is not just technical, it is human. It explains why we can live in a world of stability even as the universe grows. It shows why stars shine in galaxies instead of drifting into mist. It reveals why the night sky is patterned with clusters and filaments rather than spread uniformly with light. Expansion does not erase order. It creates a cosmic stage where order persists within islands, while the stage itself grows larger. The chapter moves now toward its final step, the recognition that this balance between bound and unbound is not fixed, but shaped by dark energy, the force that accelerates expansion. To see the full picture, we must examine how dark energy alters the boundary, tipping the scales ever more towards stretching and raising the question of whether even the most tightly bound systems may someday yield. The separation between bound and unbound systems is not only a matter of physics, but also of destiny. When we ask what will happen to the structures of the universe over vast stretches of time, the answer depends on where this line is drawn and how it shifts. Gravity guarantees that atoms, planets, stars, and galaxies remain intact against the faint stretching of space. But expansion guarantees that the distances between galaxy groups widen, pulling the larger web of the cosmos apart. This duality is the key to understanding both the beauty of the present universe and the solitude of its future. In the local group, the Milky Way and Andromeda galaxies will merge in several billion years. Their stars will dance in slow gravitational orbits, their dark matter halos combining to form a new giant elliptical galaxy. Expansion has no power here, for gravity has locked this system together. But as this drama unfolds locally, the larger universe drifts further away. The great clusters we see today, Virgo and Coma and countless others, will grow fainter with every passing eon. Their light will stretch into longer wavelengths, fading into invisibility. Eventually, they will disappear beyond a horizon set not by distance in the ordinary sense, but by the accelerating expansion of space-time. The contrast is striking. On one hand, galaxies collide, stars are born, and bound systems continue their intricate choreography. On the other, the canvas upon which they are painted grows larger, pushing everything beyond reach. The cosmic web itself thins as filaments stretch and voids widen. What remains visible from within each bound island is only a fraction of the universe that once was. The line between bound and unbound is not just a technical boundary. It is a horizon that separates what can remain part of our story from what slips into silence. This horizon has profound implications for human understanding. The galaxies we now observe with telescopes are messages from the past, light that has traveled for billions of years. But in the far future, many of those messages will no longer arrive. Civilization, if it endures, may look into the night sky and see only the stars of its own galaxy, unaware of the broader universe we know today. The knowledge we hold is itself temporary, a gift of timing. We live in an era when the cosmos is still open to our eyes, when light from distant galaxies still finds us. Future observers may not have that gift, and without it, the story of cosmic expansion may remain hidden. To grasp the human meaning of this is to see ourselves as living in a privileged epoch. We stand on Earth, bound to the Sun, orbiting within the Milky Way, itself part of a bound group. Yet beyond our island, the universe is already slipping away. Our ability to know the cosmos is tied to the present, to a time when bound and unbound are still within sight of one another. To lose that connection would be to lose an awareness of our place in the vastness. Knowledge, too, is bound by expansion. The narrative of bound and unbound systems is therefore not only about galaxies and clusters, but about the fate of meaning itself. The expansion of the universe sets limits not only on what is visible, but on what can be known. It shows us that permanence is relative, that bonds endure for a time, but not forever, that even the strongest anchors are set within a stage that changes. Expansion and gravity do not simply shape the cosmos, they shape the possibility of understanding the cosmos. And so, this chapter closes with a realization that deepens the mystery. Bound systems endure because their forces overwhelm expansion, but expansion is patient and relentless. carving away everything that lies beyond their reach. What remains in the end is a patchwork of islands in an ocean of emptiness, each carrying its own story, each cut off from the rest. To know this is to glimpse not only the physics of the universe, but its poetry, the way permanence and impermanence weave together in the great design. The next chapter steps into the force that drives this separation to ever greater extremes, dark energy. For it is not enough that space stretches, it stretches faster and faster, pushed by a presence that resists comprehension. If bound and unbound define the present, dark energy defines the future, and its influence may decide the ultimate fate of everything that exists. In the final years of the 20th century, astronomers set out to measure the fate of the cosmos. They believed the answer lay in the light of dying stars, brilliant supernovae scattered across distant galaxies. These explosions, Type 1 as supernovae, are so luminous that they can be seen halfway across the universe. They also burn with nearly the same intrinsic brightness, allowing them to serve as cosmic mile markers. By comparing how bright they appear to how bright they should be, astronomers could determine their distances. By comparing that distance to their redshift, they could measure how the universe has expanded over time. The expectation was simple. Gravity pulls matter together. Over billions of years, expansion should slow, just as a ball thrown upwards slows against Earth's pull. Some thought the universe might expand forever, gradually decelerating, but never stopping. Others thought gravity might eventually win, reversing expansion into a collapse, a future big crunch. But few considered what the data actually revealed. The supernovae were dimmer than expected. They were farther away than they should have been if expansion was slowing. The conclusion was inescapable. The expansion of the universe was not slowing down, it was speeding up. This discovery, announced in 1998 by two independent teams, shook cosmology to its core. Something unseen was pushing galaxies apart with increasing strength. The name given to this phenomenon was dark energy. It was not energy in any familiar sense. It did not radiate, it did not interact, it did not clump. It was a property of space-time itself, a kind of negative pressure that caused expansion to accelerate. In the equations of relativity, it appeared as the cosmological constant, the very term Einstein had once inserted and later dismissed as his greatest mistake. Now, it returned as the most plausible explanation for the data. What is dark energy? We do not know. We only know its effect. It constitutes roughly 70% of the total energy density of the universe, dominating over both ordinary matter and dark matter. Its presence is revealed not only in supernovae, but also in the patterns of the cosmic microwave background and the large-scale distribution of galaxies. All the evidence points in the same direction. The universe is not only expanding, it is accelerating, driven by an invisible component that permeates all of space. The human meaning of this is staggering. For centuries, we imagined gravity as the universal binder, the force that shapes stars and galaxies, the architect of order. But now we see that gravity has a rival. Dark energy does not pull, it pushes. It acts not to gather, but to disperse, not to bind, but to separate. It is, in a sense, a cosmic anti-gravity. It does not erase gravity locally, but it tilts the balance on the largest scales, ensuring that the universe will not collapse, but will instead expand faster and faster with time. The mathematics is captured in the Friedmann equations, where the density of matter and radiation competes with the effect of the cosmological constant. If matter dominates, expansion slows. If dark energy dominates, expansion accelerates. Today, observations show clearly that dark energy has taken the lead. Matter becomes more dilute as the universe grows, but dark energy remains constant in density, an unchanging property of space itself. As a result, its influence grows with time, ensuring that acceleration will continue and increase. Philosophically, this is a revelation. The universe is not balanced between two fates, collapse or eternal drift. It is instead driven toward acceleration, toward a future where galaxies slip beyond one another's horizons, where isolation deepens, where the night sky grows empty. Gravity, though it sculpts local structures, is fated to lose on the cosmic stage. The expansion does more than stretch space. It changes gravity's influence, reshaping the destiny of the universe itself. To live in such a universe is to live in a cosmos where permanence is fleeting. The bonds that matter weaves remain, but the context shifts. Galaxies endure, but their neighbors vanish. Clusters hold, but the voids widen. The web of the universe stretches thinner as dark energy pushes harder. The story of bound and unbound is rewritten by this mysterious presence, and with it, our understanding of what it means for the cosmos to hold together. And so we stand at a threshold. We know dark energy exists. We can measure its effect, but its nature remains hidden. Is it truly a cosmological constant, unchanging for all time? Or is it something more dynamic, a field that evolves with the universe? Could it decay, shift, or transform, altering the fate of everything? These questions remain unanswered. What we know is that dark energy is real, and it changes everything. The next part of this story explores not only its discovery, but its consequences, how it reshapes the balance between gravity and expansion, and how it defines the very destiny of the cosmos. Dark energy changes not only the fate of the universe, but also the way we think about balance itself. For centuries, gravity had seemed the unquestioned master of cosmic structure. It gathered dust into stars, stars into galaxies, galaxies into clusters. It wrote permanence into the sky. But the discovery of accelerating expansion showed that gravity is not the only great shaper. Dark energy works in silence, invisible and intangible, and yet it dictates the ultimate trajectory of the cosmos. To imagine how it acts, think again of the balloon analogy, but with a difference. As the balloon inflates, the surface stretches faster and faster, as if an unseen hand pushes not only steadily, but with increasing strength. This is what dark energy does to space-time. It does not diminish as the balloon grows larger. It stays constant, a pressure that keeps driving the fabric outward. Matter becomes thinner, galaxies more separated, but the push of dark energy does not fade. Indeed, it becomes more important as matter thins, ensuring that acceleration dominates the universe's story. Some cosmologists interpret dark energy as the cosmological constant, a term that represents energy inherent to empty space. Even when all matter is removed, space itself carries energy. Others imagine it as a dynamic field, something that may change with time, perhaps growing stronger or weaker, perhaps even reversing. This possibility raises profound questions. If dark energy increases, could it one day overwhelm all forces, tearing galaxies apart, then stars, then atoms in a catastrophic Big Rip? If it decreases, might acceleration slow, leaving the universe to coast quietly into a colder eternity? If it shifts form, could the cosmos experience transitions as dramatic as the ones that shaped its early history? What is known with certainty is only its effect today. Observations of supernovae, the cosmic microwave background, and galaxy clustering all confirm that dark energy dominates the present universe. Its influence is written into the very geometry of space-time. It is not an add-on, not a patch, but a fundamental component of the cosmic script. Without it, the universe would look different, evolve differently, and end differently. With it, the night sky holds both beauty and forewarning, for what we see now is only a moment in a grander acceleration. For the human imagination, dark energy is unsettling. It tells us that the familiar forces of attraction are not the whole story. The cosmos is not only held together, but also pushed apart. It tells us that permanence is not guaranteed. What feels solid and eternal is set against a backdrop that hastens separation. Even the nearest galaxies that now adorn our telescopes may one day be invisible, their light forever unable to bridge the gap. Our sense of belonging to a vast community of galaxies is itself temporary, a privilege of this era. And yet, there is wonder here. Dark energy reveals that the universe is stranger than expected, richer than any simple model. It shows us that even after centuries of exploration, there are still mysteries that reach beyond current comprehension. It forces us to recognize that the cosmos is not simply a stage for matter, but a participant with properties of its own that guide destiny. In this way, dark energy is not only a puzzle, but also a gift, reminding us that the universe is still alive with questions, still full of revelations, waiting to be uncovered. As we step further into this story, the balance between attraction and repulsion takes center stage. Gravity and dark energy are not separate actors on an empty field. They are intertwined aspects of the same geometry, one curving space to bring matter together, the other stretching it apart. The future of the universe will be written in the outcome of their contest, a contest that already tilts toward expansion. The next part of this chapter explores the consequences of this tilt, how acceleration sculpts the large-scale structure of the cosmos, slows the growth of clustering, and deepens the voids, reshaping the universe we see into the universe that will come. Dark energy is not content to remain a subtle presence. Its influence grows stronger as time unfolds, because while matter and radiation thin as the universe expands, dark energy stays constant. This constancy gives it an advantage that only increases. Billions of years ago, gravity still slowed the expansion, allowing galaxies and clusters to form. But now, dark energy dominates, and the universe has entered a new epoch, one where acceleration is permanent and unstoppable. We see its fingerprints in the structure of the cosmos. Gravity works to draw matter together, to form clusters and filaments, to build the great cosmic web. But dark energy counteracts this growth. On the largest scales, where gravity works most slowly, acceleration prevents matter from gathering. Clusters form more sluggishly than they would in a universe without dark energy, and vast voids expand more quickly. The cosmic web is frozen in a state of partial growth, forever incomplete, its filaments stretched thinner and thinner by the accelerating fabric. This interplay gives the universe its texture. Without dark energy, clustering would continue, galaxies would merge into ever larger structures, and perhaps one day everything would collapse back together. With dark energy, this vision is denied. The structures we see today are near the limit of what gravity can assemble. Future generations of stars will still form within galaxies, and galaxies will still merge within bound clusters. But the largest structures will not grow much beyond what exists already. The cosmic web has reached maturity, and dark energy ensures it will not evolve further. For human beings, this is a revelation that touches imagination as much as science. We live at a unique moment when the cosmic web is visible, when galaxies still fill the night sky, when light from billions of years ago still reaches us. But in the distant future, that vision will fade. Acceleration will push galaxies away faster than their light can travel, and the web will dissolve into darkness. Our descendants, if they endure, may look into the night sky and see only a single galaxy, unaware that countless others once shone beyond. The story of dark energy is not only about physics, it is about knowledge itself and how it is bound by time. Philosophically, dark energy represents a profound inversion. For centuries, humans imagined gravity as the universal force, the ultimate binder, the hand that holds the cosmos together. But the universe itself has revealed a deeper truth. Gravity is local, expansion is global, and dark energy ensures that the global wins in the end. It is not that gravity fails, but that its domain is limited. Within galaxies, stars still orbit. Within clusters, galaxies still gather. But beyond those islands, expansion grows unchecked, driven by a presence we cannot see and do not yet understand. The mystery remains unsolved. Is dark energy truly constant, or will it change? If constant, the universe will expand forever, galaxies drifting beyond horizons, stars aging and dying in isolation, a future of cold and silence. If it increases, the expansion may become catastrophic, tearing even bound systems apart in a cosmic Big Rip. If it decreases or reverses, a new fate may emerge, perhaps even collapse. The universe has not yet revealed which path is true. What we know is that dark energy holds the key, and its secret is written in the very fabric of space. And so this chapter closes with both knowledge and ignorance. We know that dark energy is real, that it accelerates expansion, that it reshapes the growth of structure and seals the fate of unbound systems. But we do not know what it is, why it exists, or whether it will endure. It is the most dominant component of the universe, and yet the most mysterious. To understand it is to understand the future. To fail is to remain blind to the destiny of all things. The next chapter turns from the mystery of dark energy to its consequence, the weakening of gravity over distance. Not because gravity itself changes, but because expansion increases the separation of masses, reducing their influence and slowing the growth of clustering. It is here that the subtle hand of dark energy becomes visible, not only in theory, but in the very shape of the cosmos we observe. When we think of gravity, we think of a force that holds us firmly to the Earth, keeps the planets circling the sun, and binds stars into galaxies. Its pull feels absolute, as though no distance could diminish its influence. Yet gravity is not infinite in strength. It weakens with distance, following the inverse square law that Newton first wrote and Einstein later reframed in geometry. Double the distance between two masses, and the gravitational influence falls to a quarter. Stretch that distance across light years, and the attraction becomes faint, almost imperceptible. On human scales, gravity feels strong, but on cosmic scales, expansion conspires with distance to make gravity's bonds fragile. This is where the growth of the universe reveals itself most clearly. As galaxies drift apart with expansion, their mutual gravitational pull diminishes, not because the law of gravity has changed, but because the space between them grows. Imagine two galaxies separated by millions of light years. Their pull on each other is already faint. As expansion increases the separation, that faintness grows until the attraction is too weak to draw them closer. They drift with the flow of space-time rather than against it. Gravity is constant in form, but expansion changes the playing field, increasing distances until the bonds can no longer hold. We see this in the large-scale distribution of matter. In the early universe, matter clumped efficiently. Tiny ripples in the density of the hot plasma grew into galaxies and clusters. Gravity worked swiftly because distances were short and densities high. But as expansion proceeded, matter thinned and galaxies spread farther apart. Clustering slowed, structures grew more sluggishly, voids widened, and the cosmic web became stretched. Gravity had not weakened in principle, but in practice, its ability to gather matter was reduced by the ever-widening gulf. This effect is not trivial. It determines the texture of the cosmos we observe today. Computer simulations that include both gravity and expansion reproduce the intricate filaments and clusters seen in galaxy surveys. Without expansion, the web would collapse into ever denser knots. With expansion, it stretches and freezes in partial growth. The balance of attraction and distance defines the architecture of the universe itself. For human beings, the thought carries a deeper resonance. Gravity feels eternal, a binding thread that anchors worlds. But when seen across billions of light years, its influence fades into fragility. Expansion is patient, and patience is power. Over enough time, it erodes gravity's reach, separating what once might have gathered, silencing what once might have collided. The great strength of gravity is its ability to shape locally, but its weakness is revealed across the vastness, where expansion stretches the bonds until they are too thin to matter. The next part of this chapter explores how this weakening manifests in the evolution of cosmic structure, how clusters slow their growth, how voids swell, and how expansion sculpts not only the distances between galaxies, but the very destiny of their interactions. As the universe grows older, the stage upon which gravity performs grows ever larger. In the early billions of years, galaxies assembled quickly, their mutual attractions strong enough to overcome expansion. The density of matter was high, the separations were smaller, and gravity sculpted the cosmos into a rich web of filaments and nodes. But today, and even more so in the future, expansion tilts the balance. The vastness between galaxies expands faster than gravity can bridge, and so the growth of large-scale structure slows. Astronomers measure this by mapping how galaxies cluster together across space. In a universe ruled only by gravity, clustering would increase steadily. Galaxies would fall into larger and larger superclusters, and matter would condense into denser knots. Yet observations show that growth has stalled. Superclusters do not merge into larger ones. Instead, they drift apart. The cosmic web is still visible, but it no longer grows as it once did. The distances that expansion introduces diminish gravity's ability to bind. This is not a change in the law of attraction, but the simple effect of separation. The farther the galaxies, the weaker their hold on each other. One way to imagine this is to think of a campfire on a cold night. Stand near and you feel the warmth strongly. Step back and it weakens. Walk far enough into the darkness and the fire's heat cannot reach you at all. Gravity works the same way. Galaxies near each other can still merge, drawn together despite expansion. But those far apart will never meet, their bonds too faint to resist the widening of space-time. Expansion is the distance that steals gravity's warmth, the darkness that grows between the scattered fires of the cosmos. This slow weakening shapes not only galaxies, but also the vast voids. These empty regions between filaments are not static hollows. They expand faster than denser regions, because less matter means less gravity to resist the stretching of space. Over billions of years, the voids swell while the filaments thin. The contrast grows sharper. Matter pulled into thin strings and nodes, emptiness spreading wider around them. Expansion and gravity together weave this design, one binding, the other stretching, one sculpting structure, the other hollowing it out. For human understanding, this interplay offers both clarity and unease. We can measure it with precision, trace it in computer simulations, predict how it unfolds. Yet it also tells us that the bonds of the universe are limited. Gravity may feel unbreakable here on Earth, but on the scale of galaxies, its influence is delicate, its power fading with distance. Expansion ensures that this fading is permanent, that there are horizons beyond which gravity cannot reach, that there are limits to how much of the cosmos can ever be gathered into one. This recognition reshapes the story of destiny. It means that the clusters of galaxies we see today are likely the largest structures that will ever exist. Their growth is nearly finished. The filaments will stretch, but they will not collapse further. The cosmic web is frozen in its grand design, suspended between gravity's gathering and expansion separation. For us, living at this moment, the universe still reveals its structure. But for the distant future, that structure will be hidden, galaxies carried so far apart that their light can no longer bridge the widening gulfs. As this chapter continues, we turn to the most profound consequence of this slow weakening. The universe does not simply expand. It sculpts itself into isolation. Gravity can hold what is near, but distance places a boundary beyond which bonds are broken. This boundary grows with time, and in it lies the fate of knowledge, the future of what can be seen, and the ultimate horizon of what can be known. Gravity is unyielding in its form, yet fragile across distance. Its laws do not change, but the context in which they act changes with expansion. Every mass in the cosmos pulls on every other, but when galaxies are carried farther apart by the stretching of space, that pull grows fainter until it becomes meaningless. This is why, on the grandest scales, gravity seems to weaken. Not because its essence has altered, but because separation has stripped away its reach. The consequence is a universe where clustering slows. The great filaments we see across billions of light years are remnants of an earlier era when gravity had the upper hand, when matter was closer and could gather more easily. Today those filaments persist, but they do not tighten. They stretch, they thin, they grow more delicate. The voids between them deepen, expanding faster than any gathering can resist. Gravity still binds galaxies into groups, still binds stars into orbits, but the large-scale weaving is nearly complete. The cosmic web has matured, and expansion ensures that its pattern will not grow richer. We can trace this in the history of cosmic structure. In the early universe, galaxies formed rapidly, merging into clusters, building chains across the darkness. Over billions of years, the pace slowed. Now, only nearby galaxies still collide and merge, like the Milky Way and Andromeda on their destined course. Beyond such local unions, the story of gathering has ended. Distant galaxies no longer approach each other. Their gravity is too weak compared to the stretching of space. The horizon grows, and within that horizon, isolation deepens. For human beings, this knowledge carries a quiet melancholy. The night sky dazzles with its scattering of galaxies, yet we know that this abundance is temporary. Already, some galaxies are slipping beyond reach, their light stretched into invisibility. In the far future, the weakening of gravity across distance will erase the wider cosmos from view. The stars of our galaxy will remain, but the universe will seem emptier, lonelier. The truth of expansion means that knowledge itself has a horizon, that even if life endures, much of the cosmos will vanish beyond its grasp. And yet, there is beauty in this limitation, for it shows us that we live in a privileged moment. We stand at a time when the cosmic web is visible, when the great pattern of filaments and voids can be mapped, when the weakening of gravity across distance can be measured and understood. We are witnesses to the grand balance, present in the fleeting age when the universe still reveals both its near and its far. Future generations may not have this gift, but we do. The weakening of gravity with distance does not mean gravity fails. Locally, it is still the master, holding worlds, shaping galaxies, anchoring clusters. But cosmically, expansion has the final word. It stretches the fabric wider, dilutes the density, and ensures that beyond certain scales, gravity cannot win. The universe is thus a tale of scales, a place where permanence and impermanence coexist, where gravity binds nearby, while expansion pulls the distant away. And so this chapter ends on a vision of contrast. Gravity holds the small. Expansion rules the vast. The universe is shaped by their interplay, a dynamic tension that writes both structure and solitude. The next chapter turns directly to this interplay, to the cosmic web itself, where gravity and expansion meet in their most visible form, sculpting clusters, filaments, and voids into the architecture of the cosmos. When astronomers map the distribution of galaxies across the sky, they do not find a random scatter. Instead, they uncover an intricate pattern, a vast network of filaments, clusters, and voids. This is the cosmic web, the largest structure in the universe, a tapestry woven by the competing hands of gravity and expansion. Galaxies gather into chains that stretch across hundreds of millions of light years, while between them lie great voids, empty expanses so large that they dwarf anything in our imagination. It is here, in this architecture, that the tug-of-war between gravity and expansion is most vividly revealed. The cosmic web was born in the earliest moments after the Big Bang. In the hot, dense plasma of the young universe, tiny fluctuations in density emerged. Some regions were slightly denser than others, and gravity amplified these differences. Matter flowed toward the overdense regions, forming knots that would grow into galaxies and clusters. Expansion acted simultaneously, stretching the universe outward, thinning the density, and slowing the growth of these structures. The balance between attraction and stretching sculpted the initial seeds into the great web we see today. Modern surveys, such as the Sloan Digital Sky Survey, have mapped millions of galaxies, revealing this web in stunning detail. Filaments stretch like cosmic highways, connecting clusters that gleam like city lights. The voids between them are immense, spanning hundreds of millions of light years, regions where expansion has won and matter has fled. The image resembles foam or a sponge, with dense walls surrounding vast hollows. It is not a simple scattering but a structured design, shaped by gravity's pull and expansion's push. Computer simulations reproduce this structure with remarkable fidelity. By starting with the conditions of the early universe, inserting dark matter, ordinary matter, gravity, and expansion, cosmologists can evolve the cosmos forward in time. The result is a pattern nearly identical to what telescopes observe: filaments, clusters, voids, a web stretching across the cosmos. These simulations reveal that the cosmic web is not a static picture, but a dynamic process. Gravity pulls matter into filaments and nodes, while expansion stretches the space between them. The tension of these two forces writes the geometry of the universe itself. For human beings, the cosmic web is not just a scientific concept, but a vision of grandeur. Imagine floating outside the Milky Way, looking not at stars, but at galaxies. You would see them strung together in luminous chains, scattered like jewels along invisible threads. You would drift past immense voids, regions of almost pure darkness, where expansion has swept matter away. The scale is beyond comprehension, yet the pattern is familiar. It resembles networks we know: the branching of rivers, the wiring of neurons, the connections of cities. In this way, the universe mirrors itself across scales, from the microscopic to the cosmic. And yet, the cosmic web is fragile. Dark energy ensures that its growth is slowing, that the filaments will thin, that the voids will swell. In billions of years, the web will look different, stretched beyond recognition. The structures we see today are a fleeting stage in a much longer story. Gravity shapes, expansion erodes, and together they freeze the web in a moment of partial completion. The largest clusters will remain bound, but the filaments between them will fade, leaving islands of galaxies adrift in emptiness. The cosmic web tells us not only about the past, but also about the future. It reveals that gravity and expansion are locked in an endless contest, neither absolute, both essential. It shows us that the universe is not uniform but sculpted, not static but evolving. And it places us within that web, inside a galaxy bound by gravity, connected to others along filaments, part of a structure that spans the visible universe. This chapter begins with the grandeur of the web and will move toward its destiny, exploring how the tug-of-war between gravity and expansion will shape the largest structures over billions of years to come. Gravity is the weaver of the cosmic web, but expansion is the loom upon which it is stretched. To see this balance clearly, consider how galaxy clusters form. In regions where the density of matter was slightly higher than average, gravity pulled material inward, building knots in the web. These knots grew into the massive clusters we see today, each containing hundreds or even thousands of galaxies bound together. Expansion could not prevent their birth, for gravity in these regions was strong enough to resist the widening of space. But even as clusters formed, expansion slowed their growth, limiting how massive they could become and setting the scale of cosmic architecture. Between these knots lie the filaments, slender bridges of galaxies and dark matter that connect clusters into chains. Filaments are fragile structures. Gravity gathers material along their spines, but expansion pulls outward on their length, stretching them ever thinner. Over billions of years, the filaments weaken, galaxies drifting toward the dense clusters at their ends or receding into voids. Expansion erodes what gravity builds, ensuring that the web is never finished, always caught between formation and dissolution. Then there are the voids. These vast, nearly empty regions are where expansion's influence is most obvious. In areas that began with slightly lower density, matter drained away towards surrounding filaments, leaving behind hollows that grew as the universe expanded. Voids are not passive emptiness, but dynamic features, swelling larger with every passing epoch. They are the footprints of expansion, the dark counterpart to the bright filaments and clusters. In the cosmic tug-of-war, voids are the clearest sign that expansion is winning. Astronomers measure these patterns with surveys that chart millions of galaxies across billions of light years. They find that clusters are not merging into larger superclusters. Instead, they are drifting apart. The largest bound structures are already in place, their growth largely finished. Filaments stretch but do not thicken. Voids expand but do not contract. The cosmic web is no longer evolving as it once did. Gravity continues to shape locally, but expansion sets the limits globally. This slowing of structure formation is one of the strongest pieces of evidence for dark energy. Without it, gravity would continue to build larger and larger structures, collapsing filaments into denser threads and merging clusters into ever greater knots. Instead, acceleration has frozen the web in a state of partial growth. The image we see today is not only a map of space, but a snapshot in time, a record of a universe caught between the dominance of gravity and the rise of expansion. For the human imagination, this knowledge transforms how we see the night sky. The galaxies that appear as isolated smudges through a telescope are not random. They are parts of filaments, nodes in a web, strands in a cosmic design that stretches beyond comprehension. And the dark spaces between them are not mere absence, but vast voids, swollen by expansion, telling the story of the universe's restless growth. To see the web is to glimpse the handwriting of creation itself, written in galaxies and silence, light and emptiness. Yet the web is fragile, and its beauty is temporary. The balance of gravity and expansion ensures that the cosmic design we see today will not endure. The filaments will thin, the voids will swell, the clusters will drift beyond one another's horizons. The web is a fleeting stage, a pattern visible for only a chapter of cosmic time. Future observers may not see it at all, their night skies stripped of its grandeur, their cosmos reduced to a single island of stars. The cosmic web reminds us that structure is both real and impermanent. It is the product of gravity's binding and expansion's stretching, a compromise between two forces that shape everything. And as we look deeper, we find not only a picture of the present, but a clue to the future, a vision of what will endure and what will fade. The next part of this chapter will follow that vision, exploring how this tug of war plays out in the far reaches of time, shaping the destiny of clusters, filaments, and voids. The cosmic web, though immense, is not eternal. Its future is sealed by the accelerating expansion of the universe. In the present epoch, we can still trace filaments stretching across hundreds of millions of light years, linking clusters like bridges between shining cities. We can still see voids surrounded by luminous walls of galaxies, and we can still map the web in its fullness. But acceleration ensures that this vision will fade. Over billions of years, expansion will widen the voids faster than gravity can fill them. The filaments will stretch thinner, their galaxies pulled slowly toward the dense knots at their ends, or carried outward into emptiness. The largest clusters, anchored by their immense gravity, will survive, each becoming an island universe, bound within itself, but cut off from the rest. Beyond them, the web will dissolve. The graceful structure of filaments and sheets will fade into invisibility, leaving only isolated clusters surrounded by darkness. Simulations of the far future confirm this fate. In 100 billion years, the cosmic web will no longer be visible. Expansion will have carried most galaxies beyond our horizon, their light forever lost. Only the local structures, clusters and groups tightly bound by gravity, will remain. The web will still exist in a sense, but it will be hidden from view, unreachable across the widening sea of space-time. The universe will have become a scattering of islands, each surrounded by a void that grows without limit. For human understanding, this is a profound shift. Today, the web is a map of connection. It tells us that our galaxy is not alone, but part of a structure that spans the universe. It reveals that we are woven into a cosmic design, that the Milky Way is one thread among billions. But in the distant future, that vision will be gone. Observers may see only their local cluster, unaware of the web that once stretched around them. Knowledge itself will contract, even as space expands. And yet, in this fading lies a strange beauty. The cosmic web is not permanent, but its impermanence tells a story of motion and change. It shows us that the universe is not static, but alive, that structure arises and dissolves, that permanence is an illusion even on the grandest scales. The filaments and voids we see are temporary patterns in a fabric that never rests, sculpted by gravity and stretched by expansion. They are like waves on an ocean, real, intricate, beautiful, but fleeting. The human meaning of the cosmic web is also symbolic. It mirrors the way life itself is structured, connections forming and dissolving, bonds holding for a time before distance prevails. Just as galaxies gather into filaments, so too do people form communities, networks of meaning across the void of time. The cosmic web reminds us that connection is precious, not permanent, and that to live within it is to witness a stage of the universe that will never come again. As this chapter closes, the vision of the cosmic web prepares us for the deeper question of fate. If filaments thin and clusters drift apart, if the web dissolves into isolation, then what is the destiny of gravity itself? Will it always protect the bound systems within its grasp, or will expansion someday overwhelm even those bonds? The next chapter turns to this question, exploring the fate of gravity in the distant universe, from the endurance of galaxies to the possibility of a final catastrophic undoing of all bonds. The universe we see today is filled with structure. Galaxies gleam in their billions, gathered into clusters, strung along filaments, painting the grand tapestry of the cosmic web. Gravity still binds these structures, resisting the stretching of space, holding stars in their orbits and clusters in their embrace. But acceleration ensures that this balance will not endure forever. The distant future belongs not to gravity, but to expansion, and the fate of bound systems hangs in the outcome of their endless contest. In 100 billion years, the night sky will already be transformed. Beyond the local group, most galaxies will have receded beyond the cosmic horizon. Their light, stretched into invisibility, will never reach us. Gravity will keep our local island intact, perhaps as a merged elliptical galaxy formed from the collision of the Milky Way and Andromeda, but the broader universe will vanish from view. For future observers, the cosmos will appear small and lonely, a single island in a sea of darkness. The knowledge that the universe once teemed with galaxies will be lost to their eyes. Yet within bound systems, gravity will still rule, stars will orbit, galaxies will spin, clusters will remain intact. Locally, expansion cannot undo what gravity has bound. This is the promise of permanence that general relativity allows, that gravity dominates where its strength is sufficient. Even in a universe accelerating outward, galaxies remain held, stars remain fused, planets remain in orbit. For a time, the balance ensures survival, but the story may not end there. If dark energy is truly constant, the universe will expand forever at an accelerating pace. The horizon will shrink, isolating clusters from one another until each stands alone. Over trillions of years, stars will burn out, galaxies will fade, black holes will dominate. This is the scenario known as the Big Freeze, a future where expansion continues without limit, leaving a cosmos cold, dark, and empty, yet with gravity still binding the remnants within its reach. There is, however, another possibility. If dark energy grows stronger with time, if its pressure increases rather than remains constant, then the acceleration could become catastrophic. Expansion could eventually tear apart even bound systems, overwhelming galaxies, stars, planets, and atoms themselves. This is the vision of the Big Rip, a universe that not only expands but disassembles, where no structure survives, where gravity is undone by expansion's relentless force. In this scenario, the fate of gravity is total defeat. And still, another path may exist. If dark energy weakens or decays, acceleration might cease, leaving the universe to expand more gently, or perhaps to slow once again under gravity's hand. In this case, bound systems would endure indefinitely, protected by gravity, while unbound regions continue to drift apart. The cosmos would remain a scattering of islands, but their stability would be secure. Gravity would not conquer expansion, but neither would it be destroyed. The uncertainty lies not in the mathematics, which can describe all of these fates, but in the nature of dark energy itself, which remains unknown. The universe has not yet revealed whether its acceleration is constant, increasing, or temporary. What is clear is that gravity's domain is limited, and that its future depends on the balance of forces written into space-time. The fate of everything we know, the stars above, the galaxies beyond, the atoms within our bodies, rests on the outcome of this cosmic contest. This part of the chapter begins the exploration of that fate. The next step is to dive deeper into what happens to the universe in these distant futures, to trace the consequences of the Big Freeze, the Big Rip, or eternal stability, and to understand what they mean not only for physics, but for our sense of permanence in a universe that never ceases to change. The Big Freeze is perhaps the most haunting of all cosmic destinies, not because it ends in violence, but because it ends in silence. Imagine the universe not in millions or billions of years, but in trillions. By then, the galaxies that remain bound in local groups will have long since merged into giant ellipticals, their spirals smeared into featureless swarms of ancient stars. Star formation will slow as gas is consumed, and new generations of suns will dwindle. Gravity will still hold the remnants together, but the stage around them will grow emptier with every passing epoch. As time stretches on, the stars themselves will change. Massive blue stars, which live only a few million years, will vanish first, leaving behind white dwarfs, neutron stars, and black holes. The smaller, dimmer red dwarfs will endure far longer, some burning for trillions of years, but even they will eventually exhaust their fuel. The cosmos will grow colder as starlight fades. The brilliance that once filled galaxies will dim into faint embers scattered across the dark. Gravity will continue to bind these remnants, but expansion will ensure that they remain isolated, each island a quiet graveyard of stars. Black holes will come to dominate. These titans, formed from the collapse of massive stars or from the merging of galaxies, will sit at the hearts of clusters and galaxies, swallowing what matter remains nearby. They will grow for a time, but eventually even their feast will end as fuel becomes scarce. Then begins an even stranger fate: evaporation. According to Stephen Hawking's theory, black holes slowly radiate energy through quantum processes at their horizons. For stellar mass black holes, this takes unimaginably long, but over timescales of 10 to the power of 100 years and beyond, even the largest black holes will vanish into faint wisps of radiation. Gravity will still be written into their curvature, but eventually that curvature itself will fade. In this vision of the Big Freeze, gravity does not fail catastrophically. It continues to bind stars into galaxies and galaxies into clusters, but its triumph is temporary. Expansion stretches the universe so relentlessly that bound systems become isolated beyond recovery. The gravitational bonds remain, but they are islands adrift in a sea that expands without limit. The result is a universe of silence. No new light, no new structure, no new life. Only cold remnants scattered across an endless darkness. This future is sobering, but it also highlights the remarkable timing of our existence. We live in an age when stars still shine, galaxies still gleam, and the cosmic web still connects vast distances. In the timeline of the universe, this is a brief window, a moment when both gravity and expansion still share the stage, when both light and darkness are present. The Big Freeze reminds us that what we see today is temporary, that the cosmos is not fixed, but transient, that permanence is an illusion, even on the grandest scales. And yet, there is another possibility, that dark energy does not remain constant. If it grows stronger with time, the future is not a gentle fading into silence, but a violent unraveling of every bond, a big rip where even gravity itself is destroyed. The next part of this chapter explores this more extreme vision, where expansion overwhelms not only distance, but the very structure of matter itself. The Big Rip is a vision far more violent than the quiet solitude of the Big Freeze. In this scenario, dark energy does not remain constant, but grows stronger with time. Its repulsive pressure increases relentlessly until no force in the universe can resist. At first, the change is subtle. Galaxies drift apart as they do today, but the pace quickens. The cosmic horizon shrinks, swallowing galaxies more quickly. The night sky empties faster than in the Big Freeze. But then, acceleration turns catastrophic. Billions of years from now, if dark energy strengthens, even galaxy clusters will yield. Gravity, which has held them for billions of years, will be overwhelmed. Galaxies bound together will be torn apart. their mutual attractions powerless against the accelerating stretch of space-time. Then comes the turn inward. Individual galaxies themselves will unravel. Stars, once secure in their orbits, will drift outward as expansion pries open the gravitational bonds within galaxies. The Milky Way, Andromeda, and all others will dissolve into scattered streams of stars, carried outward by the growing tide. As expansion accelerates still further, the scale of destruction shrinks. Solar systems will be next. Planets will break free of their stars, orbits ripped open by the stretching of space itself. Worlds will drift alone, their suns no longer their anchors. Gravity, the most familiar of bonds, will no longer hold. Even planets themselves will face dissolution as the expansion presses inward on smaller and smaller scales. Eventually, should dark energy continue to grow unchecked, even atoms will be torn apart. The electromagnetic force binding electrons to nuclei will succumb, and matter itself will dissolve. Protons and neutrons, the building blocks of the atomic nucleus, may be ripped apart as well. The very fabric of matter would unravel, leaving only a thin soup of elementary particles scattered into an expanding void. Gravity will have long since lost its contest. Every bound system surrendered to the growing power of expansion. The Big Rip is not certain. It depends on whether dark energy changes with time, whether its pressure strengthens rather than remains constant. Observations so far suggest that it behaves like a cosmological constant, unchanging and eternal. But the possibility remains, written into the equations, that it may vary. If so, the future could be far more violent than the gentle fading of the Big Freeze. In the Big Rip, there is no permanence at any scale. Nothing survives. Philosophically, this scenario is both terrifying and profound. It tells us that even the strongest forces we know may one day fail. It tells us that bonds we take as eternal, galaxies, stars, atoms, are fragile against the deeper dynamics of space-time. And it tells us that expansion is not merely a backdrop, but a force of destiny, capable of rewriting the structure of reality itself. To imagine the Big Rip is to imagine the ultimate defeat of gravity, the undoing of all coherence, the return of the universe to silence through violence. Yet even if this fate is not realized, the question it poses remains. Can gravity ever truly endure? It binds the local, but expansion rules the global. It holds for a time, but expansion stretches without limit. The fate of the universe hangs on this balance, and the answer lies in the unknown nature of dark energy. Until that mystery is solved, the destiny of gravity remains an open question, suspended between the quiet cold of the Big Freeze, the catastrophic undoing of the Big Rip, or the stable endurance of bound systems in a cosmos that stretches forever. And so this chapter closes with uncertainty, but also clarity. The universe is not static, and gravity is not absolute. The future is not written in permanence, but in contest. Expansion grows, gravity holds, and their struggle shapes not only the cosmos we see, but the destiny we cannot yet know. The next chapter turns to a special case within this drama. Black holes, the strongest expressions of gravity, and how they fare in a universe that never stops expanding. Black holes are the most extreme expression of gravity, regions where space-time is curved so deeply that nothing can escape. Not light, not matter, not even information beyond their horizons. They stand as monuments to Einstein's vision of gravity, the places where geometry itself folds inward. If gravity can endure anywhere, it should be here, at the hearts of galaxies, where black holes millions or billions of times the mass of the sun anchor the cosmos. But how do these titans fare in a universe that expands without end? At first glance, expansion seems irrelevant to black holes, Their horizons are defined locally, set by the mass within them. Space may stretch across billions of light years, but near a black hole, the curvature is so strong that expansion has no influence. The event horizon remains the same size, determined by the Schwarzschild radius or by more complex formulas for rotating black holes. The immense pull of gravity dominates over any gentle stretching. For this reason, black holes do not expand with the universe. They are insulated by their own geometry, fortresses of curvature, untouched by the widening of space outside. And yet, they do not live outside the cosmos entirely. Black holes feed on their surroundings, swallowing gas, stars, even entire companion black holes. In the early universe, when matter was abundant, they grew rapidly, lighting the sky with quasars so bright they could be seen across cosmic time. But as expansion carries galaxies apart and thins the cosmic web, the fuel supply dwindles. Black holes may still merge within bound systems, but beyond those islands, there is nothing left to consume. Expansion writes limits into their future by starving them of matter. Then, there is the slower, quieter process of Hawking radiation. Though black holes appear to trap everything, quantum mechanics allows for a faint leakage at their horizons. Over unimaginable spans of time, this radiation carries away mass, causing black holes to evaporate. For stellar mass black holes, the timescale is far beyond the current age of the universe. For the supermassive black holes at galactic centers, the lifetime is even longer, stretching to 10 to the power of 100 years or more. Yet even these giants will not endure forever. Expansion may not undo them directly, but time itself ensures their demise. In this sense, the fate of black holes mirrors the fate of gravity itself. Locally, they resist expansion, their horizons unmoved by the stretching of space, but cosmically, they cannot resist isolation. The galaxies around them fade beyond horizons, the stars within them burn out, and in the end, evaporation carries them away. Expansion sets the stage for their solitude, and time delivers their end. For human understanding, black holes symbolize permanence, the final state of collapsed stars, the unyielding grip of gravity. To know that they too are impermanent is to glimpse the deeper truth of the cosmos. Nothing lasts forever, not galaxies, not stars, not even the darkest shadows of space-time. Expansion and entropy together ensure that all structures fade. Black holes are the last to remain, but even they cannot escape the tide of time. This part of the chapter has opened the question of how black holes interact with expansion. The next step is to trace their full journey through cosmic history, from their fiery births in collapsing stars, through their reign as engines of galactic cores, to their slow fading in an accelerating universe. In that journey, we find the ultimate expression of gravity's triumph and its eventual surrender. In the beginning, black holes were born from death. The first stars in the young universe, enormous and short-lived, collapsed under their own gravity after only a few million years, leaving behind black holes of stellar mass. These were seeds. In the dense environment of the early cosmos, where galaxies formed quickly and gas was abundant, the seeds grew. They devoured matter from their surroundings, merged with one another, and in time became supermassive, millions to billions of times the mass of the Sun. Their hunger lit the universe with quasars, beacons visible across billions of light years, powered not by the black holes themselves, but by the matter spiraling into them, heated to incandescent brilliance before vanishing across their horizons. During this era, expansion was not yet dominant. The universe was denser, and gravity had more sway. Black holes grew easily, fed by rivers of gas along filaments of the cosmic web. Their reign was dramatic. Galaxies formed around them, their centers dominated by these titans. The balance of power favored gravity then, and black holes flourished as its greatest expression. But as billions of years passed, expansion changed the landscape. Galaxies drifted farther apart, gas supplies dwindled, and black holes grew quieter. Many still merge when galaxies collide, but the opportunities become fewer. Instead of blazing quasars, most black holes now lie dormant, visible only by the occasional flare of matter falling inward. They remain immense, but they are no longer fed. Expansion has not destroyed them, but it has starved them, isolating each within its galaxy, and in the far future within its cluster, until nothing remains to sustain their growth. Even in solitude, black holes endure. They are the last strongholds of gravity, places where space-time curves inward so deeply that not even expansion can intrude. Locally, they are immune to the stretching of the cosmos, yet they are not immune to time. Hawking radiation ensures that they leak, slowly but inevitably, shedding energy across incomprehensible spans. A stellar mass black hole takes far longer to evaporate than the universe has yet existed. A supermassive black hole lasts longer still, persisting for timescales so vast they dwarf all human imagination. But given enough time, every black hole fades. Expansion sets the stage by isolating them, and then time writes their final chapter through evaporation. What does it mean that even black holes are impermanent? For human beings, they symbolize finality, the absolute triumph of gravity. They are the end state of collapse, the most extreme possible objects. And yet, physics tells us they are not eternal. Expansion may not unmake them directly, but it ensures that the universe around them grows colder and emptier, while Hawking radiation ensures that even their shadows dissolve. This truth reveals a cosmos where nothing escapes impermanence, where even gravity's ultimate expression is destined to fade. The next part of this chapter will follow black holes into the farthest reaches of time, exploring their evaporation in the deep future of an accelerating universe, and asking what remains after the last of them has gone. In their story lies the final fate of gravity itself, written across horizons that endure long after all else has vanished. In the deep future of the universe, long after the last stars have burned out and the last galaxies have merged into solitary islands, black holes will remain as the dominant structures. For trillions of years, they will rule the cosmos in silence, their horizons marking the boundaries of no return. They will be the final monuments of gravity, enduring long after light has faded and matter has thinned. Yet even these titans cannot escape the slow, patient erosion of time. Hawking radiation ensures that black holes are not eternal. At their event horizons, quantum fluctuations produce pairs of particles, one falling inward, the other escaping outward. To an outside observer, it appears as though the black hole is radiating energy, losing mass in the process. For stellar mass black holes, this evaporation takes 10 to the power of 67 years. For supermassive black holes at the centers of galaxies, the timescale extends to 10 to the power of 100 years or more. These numbers defy comprehension, but in the language of the universe, they are finite. Given enough time, even the greatest black holes will vanish. As they evaporate, the process accelerates. A black hole loses mass slowly for most of its life, but as its mass shrinks, the radiation grows stronger, the temperature rises, and the final stages are violent. The last moments of a black hole's life are a sudden burst of energy, a release of what has been trapped for eons. Afterward, nothing remains but faint radiation spread thinly across the expanding void. Gravity, once absolute within the horizon, surrenders completely. When the last black hole evaporates, the universe enters a new stage, sometimes called the Dark Era. No stars shine, no galaxies exist, no black holes remain. The cosmos is filled only with a thin bath of particles and radiation, stretched ever thinner by expansion. Gravity has no structures left to shape. The mighty hand that sculpted galaxies, bound stars, and created horizons is quiet. Expansion alone carries the universe forward, pulling what remains into greater emptiness. The story of black holes in an expanding universe is therefore both triumphant and tragic. They resist expansion locally, impervious to the stretching of space. They endure for timescales beyond imagination, outlasting stars, galaxies, and clusters. But they cannot resist forever. Expansion starves them of matter. Time erodes them with radiation, and in the end, they too vanish. Their fate is the fate of gravity itself, powerful, creative, enduring, but not eternal. For humanity, this vision is both humbling and profound. To look at a black hole today is to see the strongest expression of gravity, a place where space-time itself falls inward. To know that even these giants will someday fade is to glimpse the impermanence of all things. The universe is not a story of permanence, but of change, not of eternal bonds, but of temporary triumphs. Gravity wins for a time, but expansion and entropy claim the future. And yet, within this impermanence lies beauty. The fact that we can see black holes now, that we can measure their shadows and detect their mergers, means that we live in a moment when gravity's might is still visible. The cosmos has granted us a chapter when the grand structures remain, when the horizons of black holes still stand as monuments. To know their fate does not diminish their wonder. It enhances it, reminding us that we are witnesses to a fleeting age in a universe that never ceases to evolve. With the fading of black holes, the stage is set for the end of time itself. Expansion carries the remnants into silence, while gravity, once the master of structure, withdraws into memory. The next chapter turns not to the physics of matter, but to the story of human understanding, to how our species has come to know these truths, and how the interplay of gravity and expansion has reshaped our vision of permanence and change. The story of gravity and expansion is not only a scientific narrative, it is also a human one. For millennia, people gazed at the sky and imagined it as a perfect dome, eternal and unchanging. The stars seemed fixed, the planets wandered slowly, and the sun returned predictably each morning. To the human eye, the cosmos was permanent. Gravity, as we now understand it, was invisible then. Expansion, unimaginable. What people saw was stability, and they built myths and philosophies on that vision of permanence. It was Isaac Newton who first gave the cosmos a law that connected Earth to the heavens. With his law of universal gravitation, he showed that the same force that makes an apple fall keeps the moon in orbit. The sky was no longer separate from the Earth, but governed by the same rule. To the human imagination, this was revolutionary. The universe became a connected whole, ordered by a single invisible pull. Gravity became not only a physical force, but a symbol of coherence, a reassurance that the cosmos was bound together. Centuries later, Albert Einstein would dissolve that certainty and rebuild it into something stranger and deeper. Gravity, he showed, is not a force but the bending of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. The sun does not pull on the Earth. The Earth follows the straightest possible path through a curved geometry. This vision was unsettling, yet it matched reality with elegance. The eclipse of 1919 confirmed it. And suddenly, the universe seemed far more fluid, far less permanent than Newton's orderly machine. Then came Hubble's discovery that galaxies were not fixed but receding, that the universe was expanding. With that, even the stage of the cosmos was no longer stable. Space itself could grow. The assumption of permanence gave way to the recognition of change, not only in objects, but in the very fabric they inhabit. The cosmos was not eternal in its form. It had a past, and it would have a future. The human vision of stability dissolved into a story of birth, growth, and transformation, on scales that dwarfed all previous imaginings. In the late 20th century, the discovery of dark energy shifted the vision once again. The universe was not only expanding, it was accelerating. Space was not merely stretching, it was being pushed apart by a mysterious presence with no clear origin. Gravity, once the unquestioned master, was revealed to be limited in its rule. Expansion, once thought to slow, was revealed to be speeding up. The human story of permanence was replaced with one of impermanence, of bonds that hold only for a time, of horizons that erase the past and isolate the future. Each of these discoveries reshaped not only science but human thought. Gravity became a metaphor for belonging, for the invisible ties that hold us together. Expansion became a metaphor for impermanence, for the drift that separates all things. Together, they challenged the human instinct to see the universe as a stage set forever. Instead, they revealed it as a process, a dance between binding and release, between holding on and letting go. This part of the chapter has opened the human story, from myth to Newton, from Einstein to Hubble, from dark energy to the present. The next step is to explore how these revelations altered not only physics, but the way we see ourselves in the cosmos. How the contest between gravity and expansion reshaped our sense of permanence and meaning. Human culture has always responded to the shifting vision of the cosmos. When Newton revealed gravity as the invisible thread that unites earth and sky, it gave rise to a new sense of order. The universe became a great clockwork, precise and mechanical, a system where every part obeyed the same rule. For centuries, this vision defined the human understanding of permanence. The stars were distant but bound, the heavens vast but governed by law. Philosophers and poets alike found comfort in the notion of a cosmos ordered by gravity, a place where everything belonged to the same whole. Einstein's relativity altered that comfort. Suddenly, the cosmos was no longer rigid but flexible, no longer a clock but a fabric. Space could bend, time could stretch, light could curve. The vision was more beautiful, but also more disquieting. Stability gave way to fluidity. For the first time, permanence seemed uncertain not only for matter, but for time itself. Human imagination struggled to adapt. Artists saw in relativity the bending of perception. Writers drew metaphors of warped realities, and philosophers grappled with the unsettling idea that time was not absolute. Gravity was still the thread, but the fabric it wove was not eternal. It was alive and mutable. Hubble's discovery deepened the transformation. The revelation that the universe was expanding overturned millennia of human assumption. The cosmos was not static. It had been smaller in the past. It would be larger in the future. This meant that the universe had a beginning, a moment of birth in the Big Bang. For the first time, human beings faced a cosmos with a history, not a timeless dome, but a narrative unfolding across billions of years. Culture responded with awe and unease. The idea of creation was no longer confined to myth, but written into physics. The permanence of the sky dissolved into a story of motion and change. Dark energy unsettled the human imagination even further. If expansion was slowing, perhaps gravity would win in the end. Perhaps the universe would collapse into a final embrace. This vision, though terrifying, still suggested a cycle, a return, a permanence of pattern. But acceleration broke even that hope. The universe would not collapse. It would not cycle. It would drift apart faster and faster, leaving galaxies isolated, horizons shrinking, knowledge itself eroded. The cultural weight of this discovery was immense. It told humanity that not only are we temporary, but so too is every bond, every connection. every light in the sky. The permanence of meaning itself seemed to dissolve into impermanence, and yet the human spirit responded with resilience. Writers, filmmakers, and philosophers found new metaphors in the interplay of gravity and expansion. Gravity became the image of belonging, of love, of the forces that hold families, societies, and lives together. Expansion became the image of separation, of time's drift, of the inevitability of change. In this way, science and culture entwined, each reflecting the other. The cold truths of cosmology became mirrors for the human condition. For scientists themselves, the discoveries transformed not only equations, but worldview. To study gravity was to glimpse permanence in its strongest form. To study expansion was to confront impermanence at the largest scales. Together, they taught humility. Humanity is small, bound to a single planet, yet capable of understanding the forces that shape the cosmos. That knowledge is fleeting, but it is real, a gift of the present age when the universe still reveals itself. As this part closes, we see how each step in understanding, Newton, Einstein, Hubble, dark energy, reshaped not only physics but human meaning. The next part will carry this reflection further, to the present moment, asking how our awareness of gravity and expansion changes the way we live, how it reframes our sense of permanence, and how it guides us toward acceptance of impermanence as part of the cosmic story. The story of gravity and expansion is not only the history of science, but also the story of how humanity has come to understand its place in the cosmos. Today, we stand at a moment when the truths of physics have dissolved the illusion of permanence that guided human thought for millennia. We know now that every bond has a timescale, every structure a horizon, every permanence an end. Gravity may hold galaxies and stars, but expansion ensures they will drift apart. Even the strongest anchors, like black holes, eventually evaporate. Nothing lasts forever. And yet, this impermanence does not diminish meaning. Instead, it deepens it. The bonds we share, families, communities, civilizations, mirror the bonds of the universe itself. They endure for a time, resisting separation, creating beauty in their persistence. But like galaxies in filaments, they are not eternal. To know this is to treasure the present, to understand that connection is valuable precisely because it is temporary. Expansion, on the human scale, becomes a metaphor for change, for the drift of time, for the inevitability that all things evolve. Our understanding of gravity and expansion also reshapes how we think of knowledge itself. We live in an epoch when the cosmic web is still visible, when galaxies still shine beyond horizons, when the universe reveals both its near and its far. Future observers, if they exist, may not have this gift. The expansion of space will erase much of what we see today, and with it the possibility of knowing the true scale of the cosmos. This makes our moment extraordinary. We are privileged to know what we know, to glimpse the balance between gravity and expansion at a time when both are still visible. The cultural resonance of this knowledge is profound. Gravity has come to symbolize holding on, the force that binds, the anchor that resists drift. Expansion has come to symbolize letting go, the current that pulls, the horizon that separates. Together they form a story not only of the universe, but of life itself. We cling and we release. We gather and we part. The cosmos mirrors the human condition, and our understanding of it mirrors back on us. As this chapter closes, the story of human understanding stands revealed as part of the larger cosmic story. We have moved from the belief in permanence to the recognition of impermanence, from seeing the universe as a stage set forever to seeing it as a dance of binding and release. Gravity gives meaning to the bonds we know. Expansion gives meaning to their impermanence, and together they shape not only the cosmos, but the way we see ourselves within it. The next chapter draws this reflection to its conclusion. It turns from history to philosophy, from science to symbolism, asking what it means that the universe itself is a balance between holding on and letting go, and how this cosmic dance echoes in the human heart. The universe is a story of balance. On one side is gravity, the hand that binds matter, holding stars in their orbits, shaping galaxies, and anchoring clusters. On the other is expansion, the tide that pulls everything apart, stretching space, widening voids, carrying galaxies beyond each other's horizons. Neither is absolute. Both are essential. Together, they create a cosmos that is dynamic, structured, and impermanent. Locally, gravity wins. The Earth remains bound to the Sun, circling year after year. The stars of the Milky Way orbit the galactic center, held by the immense halo of dark matter. Clusters of galaxies remain intact, their members bound to one another despite the outward stretch of space. These systems endure because their bonds are stronger than the expansion across their scale. To live within them is to feel permanence, to see stability written in the motions of the sky. But cosmically, expansion wins. Beyond clusters, galaxies drift apart, their light stretched into red, their images fading. The cosmic web itself thins as voids swell and filaments weaken. The universe grows less connected with time, its vast structures dissolving into isolation. Expansion ensures that the large scale is impermanent, that the bonds of gravity cannot span infinite distances. To look at the night sky is to see both truths, the permanence of nearby orbits and the impermanence of galaxies receding into darkness. This duality is not only physical but philosophical. It tells us that holding on and letting go are not opposites, but partners, each necessary for the story of the cosmos. Without gravity, there would be no stars, no planets, no life. Without expansion, everything would collapse into a single mass, erasing structure and variety. Together they create a universe that is neither static nor uniform, but alive with change, complexity, and beauty. For humanity, this balance is a mirror. We live our lives bound by forces of connection, family, love, memory, that hold us as gravity holds the stars. Yet time, like expansion, pulls us apart, changing everything, dissolving bonds, reminding us that nothing is eternal. To live is to experience both the security of gravity and the inevitability of expansion. The universe itself is a lesson in the balance between holding on and letting go. This part of the chapter has opened the reflection on this balance. The next will explore its deeper meaning, showing how science and philosophy converge, how the cosmos becomes not only a place we observe, but a metaphor for how we live. The balance between holding on and letting go runs through the universe and through human life alike. It is written in the laws of physics and in the passing of days. Gravity shows us the necessity of connection, how matter must come together to form stars, galaxies, and the very atoms of our bodies. Expansion shows us the necessity of release, how no structure is eternal, how even the strongest bonds dissolve with time. This duality becomes a guide when reflected into human meaning. To hold on is to cherish the bonds that give life depth, families, friendships, the knowledge we discover, the cultures we build. To let go is to accept that time changes all things, that no bond is untouched by impermanence, that change is not only loss, but the opening of new patterns. Just as galaxies drift apart to reveal the wider architecture of the cosmos, so too do lives shift and change, revealing meaning not in permanence, but in transformation. Science gives this vision its clarity. Einstein showed us that gravity is not a force, but the shape of space-time, and Hubble showed us that space-time itself stretches. Dark energy, revealed that the stretching accelerates, and Hawking revealed that even black holes dissolve. These discoveries do not erase meaning, but deepen it. They show us that permanence was never the truth of the universe, that impermanence is not failure, but reality. In this truth lies beauty, for to live in a universe of change is to live in a universe that creates, evolves, and reveals endless forms before they fade. As we close the final chapter, the narration circles back to the essence of the cosmos. Gravity is the hand that holds worlds together. Expansion is the tide that pulls them apart. The universe is the story of their endless dance, a balance between belonging and release, between permanence and impermanence, between holding on and letting go. To see this is to see not only the destiny of galaxies, but the destiny of ourselves, mirrored in the fabric of space-time. At the end of this journey, we return to the beginning, to the question of whether the expansion of the universe affects gravity. The answer is both yes and no, and within that paradox lies the deeper truth of the cosmos. Locally, gravity holds firm. It binds atoms into matter, planets into orbits, stars into galaxies, and galaxies into clusters. No stretch of space can pry apart what gravity and other forces have fastened within their scales. To live within these bonds is to feel permanence, to look at the sky and believe the stars eternal. But cosmically, expansion prevails. It widens the voids, thins the filaments, and carries galaxies beyond each other's reach. It accelerates, pushed by dark energy, until horizons shrink and knowledge itself is erased. Gravity cannot bridge infinite distances. Its reach weakens with separation, and expansion ensures separation grows without end. On this stage, permanence dissolves. The universe is not a single eternal structure, but a shifting balance of bonds that hold for a time before surrendering to change. The beauty of this truth is not in despair, but in perspective. To know that all things pass is to know that their presence now is precious. To see galaxies before they fade, to study the cosmic web before it dissolves, to know that black holes still endure before they evaporate. This is the privilege of the present. We are witnesses to a fleeting chapter in a universe of endless transformation. The gift is not permanence, but awareness, the chance to see and know while the knowing is still possible. And so the cosmic story becomes a human story. Gravity is the hand that holds us to the earth, that binds us to the sun, that anchors us to the Milky Way. Expansion is the tide that reminds us of impermanence, that shows us every bond will change, that nothing is fixed forever. Together, they write the narrative of the universe, and together they mirror the narrative of life. To live is to hold on and to let go. To exist is to belong and to drift. The closing reflection is both scientific and poetic. Gravity is the hand that holds worlds together. Expansion is the tide that pulls them apart. The universe is the story of their endless dance, a dance that gives birth to stars and galaxies, that sculpts the cosmic web, that carries everything towards silence. To see this dance is to see the essence of existence itself, the balance between permanence and impermanence, between order and change, between holding on and letting go. And in that balance lies the meaning of the universe, a meaning as vast as the cosmos and as intimate as the human heart.